Hey, good morning, AP Physics 2. We are going to start today with the second part of fluids. We're going to go, let me get that to where y'all can see it. Okay, so fluid dynamics for AP Physics 2. The learning objective is I can calculate the velocity of a fluid by applying the correct formula to the problem and then solving. And the guiding question is going to be, how can I calculate the velocity of a fluid? All right. We are going to hop to the next one. Okay, so fluids in motion. Here's the thing that we're going to work on first is we've dealt with fluids that are essentially stationary or static. Now we're going to deal with them in motion. What we're going to be talking about this entire time is what's called an ideal fluid. And what that means is it's not viscous, meaning there's no internal fluid within the internal friction within the fluid itself. It's incompressible, meaning that the density of it is constant the entire time, so it doesn't change. And then the motion is not turbulent, which means there's essentially no friction or any other forces that are affecting the fluid. I'm gonna play this little video I have right here, and just so you can see what's a laminar fluid. Okay, and you'll see it looks like this isn't even moving, but watch what this guy does here in just a second. Okay, so that is a real quick just preview of what a laminar ideal fluid would look like in motion. It was really hard to tell that it was moving. We're just going to go to the next slide. Okay, so first big topic area is what's called flow rate. And flow rate is how much mass passes a given point in a unit of time. And that is going to be constant anywhere inside of a pipe. So the flow rate of fluid is constant at every given point. I'll have a next slide that'll show you that here in a second. This is also called your continuation or continuity formula. And I've got that right here. Density equals the area of the pipe times the velocity. And then that's going to be equal to the density of the fluid times the area of the pipe times its velocity at a different point. Since density is the same everywhere, we can essentially take density out, and we're left with the area of the pipe times the velocity equals the area in a different spot times the velocity in a different spot. So I'm going to pull up the next picture so you can actually see it. Again, there's that equation. We're going to go over basically the conceptual point on this, and we're going to compare 2 points in the pipe. So the first point we're going to look at is over here on the left-hand side, and we're going to compare that to a point over here on the right-hand side. So a couple things, just pause the video here for a second. What I want you to ask yourself is, where is the velocity the fastest and why? And then I also want you to ask yourself, which point has the higher flow rate or fluid flow? So pause and then come back to that. All right, now that you've unpaused, the higher fluid flow rate, the flow rate is going to be the same in all positions. So the point on the left and the point on the right have the exact same flow rate. Now the other question is, which one is the fluid moving faster? The fluid is moving faster on the point on the right. The fluid has to move faster so that all of that mass can pass through there at the same amount of time. One more picture that kind of illustrates that will be on the next slide. What do you see in a wide river over on the left-hand side versus the kind of narrow stream over on the right-hand side? And why do you think you see this? So pause and just kind of take a minute and go, okay, why am I seeing this? Okay, now that you've unpaused, the main reason why you're seeing this is because the river on the left-hand side is very wide, so it has a large area. River on the right-hand side is really, really narrow, so it has to move much faster. That's why the water looks much more turbulent and much more swift in the picture on the right-hand side. Okay, so example problem, just read through this, pause the video, and then when you're ready, I'm going to run through this example for you. So go ahead and pause. All right, now that you've written down and tried to solve this one, we're going to walk through this question together. So where you want to start is area times velocity equals area times velocity. The area, one key thing that you're going to want to think of is if they give you a radius, which they did in this question, think of radius, and to get the area, you're going to want to do the area of a circle. So that's why I have pi r squared there. And then just went ahead and plugged in the numbers that we had into both sides, and then solved for the velocity. And since the units were in centimeters per second, the unit for this would also be in centimeters per second. We're going to hop over to the next question. It's going to be another example. All right, so this example, no real numbers to this, so just read through it, pause, and then once you think you have it, go ahead and hit unpause. All right, now that you've unpaused, the answer to this one is D, so let's talk about why. So the water flows through the pipe, and then it enters a part where the area gets reduced by half. So to compensate for that, the velocity has to double. On these are the kinds of problems where if you want to put in numbers to start with, you could have used area as a 1 and the original velocity as a 1, and then it said the area gets cut in half, so area 2 would be 1/2, and you're essentially solving for velocity 2, which would be doubled or 2. All right, one more example problem. This one has some numbers with it, so you might want to jot this down and try to work through this. So go ahead and pause the video. Once you think you have that, we'll come back and take a look. All right, now that you've unpaused, I'm going to pull up the answers for that and just kind of walk you through it. What I did was I just started with the continuity equation, and I went ahead and just solved it algebraically for velocity 2 here on this step here. If you want to go ahead and plug your numbers in and then move your numbers, you can. That's up to you. And then I just plugged everything in, 10 centimeters cubed or squared for the area, the velocity, and then the other area of 5 centimeters squared. Multiplied that out and divided by 5 and got an answer of 30 meters per second. All right, so here is the next concept we're going to talk about. So this is called the Venturi effect. This is when a fluid moves through a pipe and the pipe narrows, the pressure in the narrow section is going to decrease. I'm going to show you several different images that hopefully will help illustrate that. So this one, you'll notice I've got this part over here on the left-hand side is much wider. The part in the middle narrows, and then the part on the right-hand side widens back out. So we have higher area of pressure on the left-hand side, higher area of pressure on the right-hand side because it is more wide. The inside is constricted, it's reduced down in area, so you're going to have a lower pressure in that area. Two other photos that just kind of illustrate the same thing. This time it has the gauges with actual numbers on it, but it's doing the same thing. And then this bottom image, what you'll notice is you'll see that the water in the middle doesn't go to as high of a height. The reason that happens is there's less pressure to push it up. Remember, pressure is force divided by area. If there's less pressure there, there's less force, so that liquid is not going to get pushed nearly as high in that one. So that's kind of the second concept for today. So first concept was the continuity equation, then the Venturi effect. We're going to go over Bernoulli's equation. This one is going to look really, really long. This is really a conservation of energy concept with a fluid. So this equation applies when there's a fluid in a pipe and you have a change in height. Think of this just like conservation of energy, where total energy before and total energy after are conserved. So here's the equation. I kind of want to walk through this, and I want you to think of it in terms of energy. So you'll see one arrow pop up here on the left-hand side. Hopefully when you look at that, that kind of looks like 1/2 mv squared. Well, that is essentially the kinetic energy of a fluid. You'll notice that's on both sides. So you have essentially the kinetic energy of the fluid on both sides. You also notice hopefully one other term that looks fairly similar. I've got an arrow popping up on that one. It'll rho GH. Hopefully that looks very similar to MGH, or our potential energy equation. Notice both of those show up on each side. So you have potential energy on both sides. You have kinetic energy on both sides. The one thing that was new is going to be pressure. So pressure is kind of our third way that we can store energy. I want you to think of that as almost like another way you can store energy. All right, we're going to take a look at this in an example. So You've got an example of just a little pipe, and one of the things that you'll notice is it's going uphill and it's getting constricted. So this may be, when you see a problem, this would be a time when you go, oh, okay, I'm going to use Bernoulli's equation, one of the Bernoulli's questions with some numbers and everything. So take a minute, try to work through this one. This one will be your first attempt at a Bernoulli's equation. So take a look at that and see where you think you should start. Go ahead and pause here, just try to work through it. And then when you are ready, I will walk you through the steps on how to do a question like this. All right, now that you have unpaused, we're going to walk through the solution. So the first thing you want to do is figure out the velocity of the fluid in the other area of the pipe. So you're going to use your continuation equation or your continuity equation. You have that there for you. So you're going to plug in the area and the velocities, and then we'll solve for the missing velocity. So that'll be part one. The second part is to use our Bernoulli's equation that has all of these terms in there. One thing you'll notice is height 1 is 0. So that'll actually drop out of the equation. So we're not going to have to worry about that part. So here's the next part. So we've got pressure 1, and we're trying to solve for pressure 2. So I went ahead and moved everything over. So pressure 2 is by itself, and then plugged in the numbers and then solved it. So if you need to pause it here just to take a look at how those numbers work, feel free. And then we're going to look at one more thing. It's called Torricelli's theorem. And then we are going to walk through that. All right, last new idea of this is called Torricelli's theorem. This is going to apply, this is Bernoulli's equation, but it's reduced down very, very simply. And this allows us to figure out how fast a liquid would be traveling when it leaves something with a hole in the side. So when you'll see this, you'll have something that's filled up. It'll have a hole in the side, and you'll be able to figure out what the velocity is. So V1, which is the velocity as it exits, is the square root of 2g. And then it's basically the difference in height from the spout up to the topper of the fluid. And then as that fluid empties, the height will get reduced, which means the velocity will get reduced as well. Okay, so concept question first on this, and then we'll go with some numbers. All right, so concept question first. So take a minute, kind of read through that, and then we'll come back and talk about it here in just a second. So 2 concept questions, and then we'll pause, and then we'll talk about it. All right, the answers to these, the velocity as that water drains will decrease, as will the distance it lands away from the jar it's coming out of. Now we're going to do this same concept, except this time we are going to use the numbers. We're going to have some equation. We're going to actually use the equation. So take a minute, kind of read through this, pause, and see what you come up with for the exit velocity on this one. All right, now that you have unpaused, we're just going to walk through how to do this. I've got this up here for you. So there's the equation there at the top. I went ahead and plugged in all of the numbers. You'll notice there wasn't a y1. So if you don't have a y1, you could use 0. So I just walked through those numbers there, plugged everything in there, and I got 9.9 as the velocity that it left at. If you use 10 for your acceleration of gravity, you would get a slightly higher velocity, and that's fine as well. Okay, where can you find these equations? If you are looking on your AP formula chart, you have all those equations here at the top under the fluid mechanics and thermal physics. You'll notice A1V1 equals A2V2 is right there. You'll also notice there is Bernoulli's equation, all written out for you. The only equation that's not on there is the Torricelli's equation. So I would go ahead and just add that to your formula chart or memorize it, whichever one you want to do. As a reminder, please make sure you're doing your exit tickets and Canvas for attendance, and that will wrap us up for today. Y'all have a wonderful rest of the day.